Hello students, we have been discussing the theories of failure, and in that discussion in our previous lecture we talked about maximum principal stress theory, maximum principal strain theory, and maximum shear stress theory. We also discussed in the previous lecture that some of these theories are applicable for certain kind of material, like maximum principal stress theory works quite well for the brittle material, while maximum shear stress theory is a nice theory and most widely used theory for the ductile material. Besides this, we also discussed that some of these theories work well in certain kind of a loading condition, while in other loading conditions they fail to give the results. Like maximum shear stress theory doesn't work well for the hydrostatic pressure case because it says that sigma 1 minus sigma 2 should be less than or equal to sigma et. That means difference of the principal stresses should be less than the elastic limit stress in tension. So the difference, because in the hydrostatic pressure case the sigma 1 will be equal to sigma 2, so therefore no component should fail, while actually we know that the component do fail in the case of hydrostatic pressure. So therefore that theory doesn't work in that particular application. So we now know that the maximum the theories of failures, certain theories will work good in certain situation, and while in some others will work quite well in some other situation. Now, continuing the discussion, we'll today talk about two more theories, and they are primarily based on energy. And first of them is the maximum strain energy theory. It is also known as Hicks theory. The statement of the theory says that the failure of the material is caused when strain energy per unit volume under the complex stress system reaches the value of strain energy per unit volume at the elastic limit in a simple tension test. So here in this case, instead of talking about in terms of principal stress or principal strain or maximum shear stress, which are readily obtained quantities from the Mohr circle or our principal stress formulas, we are talking about the strain energy. We already know about the strain energy. We have calculated these values for various cases, also for the three-dimensional rate of stress. So we know that the strain energy per unit volume for a three-dimensional loading case in general for a complex system can be said as 1 by 2e in bracket sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu sigma 1 sigma 2 sigma 2 sigma 3 plus sigma 3 sigma 1. Now this is the strain energy per unit volume for a three-dimensional loaded case of complex system. Now this should be less than or equal to the strain energy for the case of simple tension test. Now as in the simple tension case, you can obtain the value of sigma, the strain energy, by simply multiplying working out the area under the stress strain curve. So because the triangular area under the stress strain curve, it is half of the stress value multiplied by the strain value, and the strain can be expressed in terms of stress by sigma by E. So that gives us basically the value of strain energy as sigma Et square divided by 2E. So now these two quantities should be equal in order for a balance, and if this quantity is greater than sigma Et by square 2E, the component will fail eventually by this theory. So by cancelling out the term 2E, we will be left with this expression which is given below, and we can compute the values by calculating first the principal stresses for the given case and then finding the value of the expression and comparing it with the sigma Et square. This theory gives fairly close result with the for the ductile material, but does not give good results again for the hydrostatic pressure case. So that is something which is eluding to us at the moment. Now let's go and talk about the next theory of failure, and which is called as shear strain energy theory or the distortion energy theory. Mind it, this is different from the pure strain energy theory we have just talked about. This is the volumetric strain energy theory, strain energy per unit volume. So that compasses the volumetric as well as the distortion energy both. But here we are comparing only the distortion energy. So shear strain energy theory is basically distortion energy theory. This is also known as the von Mises and Henke theory. Okay, the another name of this theory is von Mises and Henke theory. The statement of the theory goes like this, that the elastic failure of a material takes place where under a complex stress system its energy of distortion per unit volume equals the distortion energy due to the elastic limit stresses in simple tension or compression. Okay. So here it is assumed that the part of the strain energy causes uniform extension or contraction, that means the change in volume, whereas the remaining strain energy causes the distortion. Okay, so the total strain energy is made up of two components. One is the strain energy due to change in volume, and the other is the strain energy due to distortion. So that is the total strain energy utilization. So part of it will be used for the changing the dimension in terms of increasing the length or decreasing the length and so on and on, and the another part is used in the distortion, basically because of the shear deformations. So it is the primarily this distortion energy which is causing the failure. This is the primary emphasis of this theory. So from the above this, we can say that the total strain energy is sum up of the strain energy due to change in volume plus the strain energy due to the distortion. We have just in the last slide we have just talked about the total strain energy per unit volume, that is given by the expression 2. Now okay, now we can say that the average stress value which is causing the volumetric strain energy is basically obtained by summing all these principal stresses and dividing it by 3. Now the principal strain values, we already know these expression for the principal strain values in terms of principal stress, like epsilon 1 is given by sigma 1 by E minus mu times divided by E into sigma 2 plus sigma 3, and so on for the epsilon 2 and epsilon 3. If you sum up all these three strain values, you can simply add them, epsilon 1 plus epsilon 2 plus epsilon 3. This will give you 1 upon E minus 2 nu divided by E into sigma 1 plus sigma 2 plus sigma 3. And the average strain value will be 1/3 of this. So you just divide it by 3 and you obtain the average strain. So what you have done, you have obtained the average stress and average strain in terms of the principal stresses sigma 1 and sigma 2 and sigma 3. Now the work done due to distortion in one direction will be simply half of stress into strain. So you take the average values of the stress and average multiplied by the average value of strain and multiplied by half. That gives you the work done in one direction, and work done in all the three directions if you taken together, then you need to multiply it by 3. So 3 times the work done in one direction will give you the expression as 1 by 6e into 1 minus 2 nu into sigma 1 plus sigma 2 plus sigma 3 whole square. Now this is because the work done in all the three direction in deformation is basically nothing but your volumetric strain energy. So that is equal to uv. So uv can be given by the expression which is given here, and now you know that your deformation energy or the distortion strain energy will be the total strain energy minus the volumetric strain energy. So you write the expression for the total strain energy here, and you subtract from it just computed value of the volumetric strain energy, and then you finally obtain the distortion energy in the form of 1 plus nu divided by 6e into and by the multiplied by the bracketed expression. So you just need to simplify the above expression in order to obtain the expression which is given in equation 5 here. Now to obtain the distortion energy at elastic limit, you simply have to consider sigma 2 and sigma 3 are 0, because we are talking about simple tension test, so the stress is being applied in only in one direction. So for sigma 1 you substitute sigma et, and for the rest of the quantity sigma 2 and sigma 3 you substitute 0, and that's how you obtain the strain energy expression for distortion in a simple tension test by 1 plus nu divided by 3 into sigma et square. Now you are going to compare the expression 5 and 6. So you equate 5 and 6, and then by cancelling out the terms of these coefficients, 1 plus nu divided by e into 1 plus nu divided by e. So if you cancel it out, and 3 is cancelled by here, it will give you 2. So that is what finally you will get here. So this is the expression that you are going to obtain for this case. And if you say that okay, the left hand side expression should be less than or equal to the right hand side expression in order for the component to be safe, and if the left hand side expression is greater than or equal to sigma et square, the component is going to get failed. This theory works quite good for the ductile material as well as for our other cases. And this is the second theory which is more commonly used after our shear stress maximum shear stress theory. So one for the ductile material, one theory that is more popular, the most popular, is the maximum shear stress theory, and another theory which is used is the distortion energy theory, which also works quite well here. And you must notice that the distortion energy theory is also based on the shear stress, means shear deformation. So that's why it works quite good for the ductile material. Okay, now the time is for doing one numerical here. So what we have here is you are given in a plane element which is subjected to the stresses as shown in the figure. What are the stresses which are being applied? In the direction x, you have the 100 Newton per millimeter square load that is being applied. It is the tensile stresses which are being applied. In the direction y, there is 80 Newton per millimeter square stress that is being applied. And apart from that, you have the tau xy, the shear stress in the plane xy, given by 50 Newton per millimeter square. So these are the three stress to which the component is being subjected. There are two tensile stresses in the x and y direction each, and then there is a shear stress of 50 Newton per millimeter square. You are given the Poisson's ratio value as 0.3. You are given that the material have the elastic limit stress value as 200 Newton per millimeter square, and the modulus of elasticity for the material is given by 200 into 10 to the power 3 Newton per millimeter square. So these are the data which are given to you. Now in this numerical, you are expected to calculate the principal stresses and maximum shear stress, which you can very easily do either using the Mohr circle or directly using the formula. And the second part, you are required to calculate the factor of safety depending upon the maximum principal stress theory, maximum principal strain theory, maximum shear stress theory. So you need to calculate the factor of safety, that how much the values of the principal stress in comparison to, let's say, the elastic limit stress, and the maximum principal strain that is calculated with the elastic limit strain, and so on and on. So let's start with the first part of this numerical, that means to calculate the principal stresses and the maximum shear stress values, and which is quite straightforward because you know the formula for principal stress as sigma x plus sigma y by 2 plus minus under root sigma x minus sigma y by 2 whole square plus tau xy square. You substitute the value of sigma x and sigma y and tau xy in the expression, and you compute the values of the sigma 1, the first principal stress, and the second principal stress as 141 and 39 Newton per millimeter square. To compute the maximum shear stress, either you compute the value here, which is in the under root expression, or you simply compute sigma 1 minus sigma 2 by 2, because as you have already obtained the value of two principal stresses, you just need to make the difference of them and divide it by 2 to obtain the maximum value of shear stress, which in this case work out to be 51 Newton per millimeter square. Now comes the part second of the question. In the second part, we need to calculate the factor of safety based on the maximum principal stress theory. This is the first part of the here. So you need to compare the value of the elastic limit stress in tension with the principal stress, maximum principal stress that you have computed. So because the maximum principal stress theory says that the maximum principal stress in the component, if it exceeds or becomes equal to the elastic limit stress in the simple tension, the material is going to fail. So you are simply going to compare these two values. So as we have here the elastic limit stress defined here in the question as 200 Newton per millimeter square. So you divide 200 by the maximum value of principal stress that you have computed. So 200 divided by 141 will give you the expression as 1.42. So this is the factor of safety that we have from the failure. Now comes the second part, that is using the maximum principal strain theory to calculate the factor of safety. So in order to calculate that factor of safety, first we need to calculate the maximum principal strain, and because we have a two-dimensional state of stress, so the formula will be simply sigma 1 by E minus mu by E divided by sigma multiplied by sigma 2. So that you put it here, and then I have just not given the value here for the, I have not put the substituted the value of the modulus of elasticity, because we are going to calculating the ratio in terms of the factor of safety, so it will get cancelled out. So just I have left it like this. So you compute the value of maximum principal strain in this case as 129.3 divided by Young's modulus value or modulus of elasticity value E. Strain at elastic limit will be the stress value in the tension, that is given as 200 Newton per millimeter square, divided the value of modulus of elasticity. I just kept it again as E, so 200 by E. So in order to obtain the factor of safety, you need to divide the value of 200 by E with that 129.3. So it is basically dividing 200 with the 129.3, and this will give you the factor of safety value as 1.545. Now the last part of this is to calculate the maximum factor of safety as per the maximum shear stress theory. We know that the maximum shear stress for a unidirectional loading, that is a simple tensile test, value will be half of the elastic limit stress value. So that's why it will be 200 by 2, that is the maximum shear stress value in the simple tension, and you divide with the value of the maximum shear stress you calculated for this case 51. So you get the maximum shear stress, the factor of safety based on the maximum shear stress theory as 1.96. So you see here your maximum shear stress theory is providing you highest factor of safety. Okay, so it is telling you, okay, the component is safe, you can load it further even. Okay, so it is the actual meaning of that. While it is the maximum principal stress theory, it is telling you, okay, no, the factor of safety is only 1.42, so you can't load it much more. If you load it, it will exceed the value of the safe values quite faster. So in that terms, I would say that the maximum principal stress theory is the most conservative one, and it will give you the least values in terms of allowable stresses of sigma x, sigma y, tau xy, which will be permissible here. Okay, so that brings us to the end of our discussion today, and also to the end of the discussion on theories of failure. I would suggest you to go and read the do some numericals on this part as well.